So, for my presentation, or what I've been researching over the last couple months, is perovskite quantum dots. So, the reason that we're looking at perovskite quantum dots is because they're very good emitters. A lot of experimentalists have been able to get 100% quantum yields out of them, which is pretty good. But one of the issues that comes with these quantum dots is that over time they degrade because these are based on ligand passivations, and ligands have been, or the ligands for these models have shown to either, well, unbind from the surface, so it creates trap states, which over time reduces quantum yields, so they become unstable, basically. And then a popular method throughout the history of quantum dots is to try to get stable emission out of them, is you can dope them with metal or transition metal dopants like manganese 2+, which is what we did for our models here. So there's an image of the perovskite quantum dot in the upper top left, where it's the outside is the passivating ligands of the carboxylic acid and amine ligand groups, and we chose those groups because that's what's experimentally.
Please do not be discombobulated or scared. I'm going to focus camera, and when I was doing it last time, things changed on the screen.
Oh, okay.
You are lucky. Nothing bad happens.
Nothing bad yet, anyway. So we chose these because those are functional groups that are used to synthesize the quantum dots, and we just use short chains because we just need them to be passivated correctly. And then these are the elements that make up the perovskite quantum dot, so cesium, lead, if there's a dopant, manganese, and then bromide. And so, yeah, those are the two models that we looked at for this system. And where am I going to go from there? So the size of the systems, the quantum dots are about 1.5 nanometers in size. So they're a little smaller than what's typically seen experimentally, but it's the smallest we can do feasibly for the computations that we were running. And so the methods that we use for the intrinsic quantum dot, we looked at just regular vast calculations, and then we also included spin orbit coupling calculations because with lead it has a heavy spin orbit coupling just to being a big metal ion. And then for the manganese dome models, we did spin polarized calculations because since we're dealing with transition metal, it can have various spin states, and we wanted to pick those apart. And then we also included spin orbit calculations with those as well for the ground state. And then we did molecular dynamics at 300 degrees Kelvin temperature attached to the thermostat. We did that for about 1,000 ionic steps. And then for the excited state dynamics, we used red field theory. And then to get the red field theory for the non-radiative relaxations, and for radiative relaxations, we use oscillator strings to get those. So moving on to the models that we looked at. So for this column is the intrinsic perovskite quantum dot. So here would just be a regular ground state without spin orbit coupling attached. It would basically look the same as if we looked at the spin orbit coupling dose, except the band gap would be wider because spin orbit coupling mostly affects the lead atom, which contributes to the valence band. So the lowest spin state will decrease the band gap just due to the splitting of the spin orbit coupling. So those were our ground state geometrized optimization for the quantum dots. And then we moved on to molecular dynamics. And then by using molecular dynamics, we can track the orbital energies through time as it goes on through the steps. And if you look at some of the peaks in the conduction band, you can see that there are states introduced inside the gap, which is usually a clear sign that there's a trap state occurring, or one of the ligands, or one or enough ligands come off of the perovskite quantum dot to introduce trap states. And then that's what this density the states plot is showing here. I just picked one of the positions along the trajectory, did a single point calculation, and there's a faint little trap state near the valence band edge. And so that kind of shows that over time you can kind of get ligands coming off, going back on. If you run it long enough, you expect some ligands to eventually fly away from the quantum dot. So from molecular dynamics, we could go on to our excited state dynamics. So for non-radiative relaxation, we use Redfield theory, and these are our Redfield tensors, which basically describe coupling between orbitals between states and the off diagonal. So if you zoomed in on the image, all the diagonals would be 0, and then states close to each other are going to have high bars, and then further away you get these decaying here. And then the very high peaks indicate that there's going to be a very high rate of non-radiative transition between orbitals. So we could see that usually it's actually the reverse. Or for typical systems, for like bulk systems, you would see that near the very high and low, or low in the valence band, high in the conduction band. Like these would be higher peaks, and then as you get towards the band gap, there would be a slower relaxation. But here we see a kind of a reverse trend, which is interesting. That's probably just due to the confinement of the quantum dot, because the orbitals are squeezed together, so there's going to be higher overlap between them. So there's going to be higher non-radiative relaxation that goes with them. And then this is just a plot showing the non-radiative relaxation for a specific excitation. So we excited from HOMO -20 to LUMO +9 at time 0, and then over time it eventually decays, and we see for the intrinsic dot, the electron relaxes to the conduction band edge a little bit quicker than the hole relaxes to the valence band edge. And yeah, MATLAB didn't spit out numbers for me yet. I kind of have to work with the software a little bit, see if I can get tables of relaxation rates for a bunch of different transitions, but that'll be in the next edition of the poster. And then for radiative relaxations, we can see that so basically how radiative relaxations are computed is at each time step here, it computes an oscillator strength, which gives a probability of transition. So you can see that for earlier time steps, there's very small energy transitions occurring in the valence band and the conduction band, like in between those states, and that's what these. This is here just showing low energy emissions over time, and then eventually once they both relax at the band edge, we get a very strong emission peak coming from the HOMO-LUMO gap, which is indicated by these two plots there. And as expected, the intrinsic quantum dot shows a very high PL, or a very high intensity for the HOMO-LUMO transition, which corresponds to what you define experimentally, very bright light transition. So that's the intrinsic quantum dot with no doping, and then we move, and then now compare that to the transition doped perovskite quantum dot. So we found from manually setting different spin orientations, we found that the system likes the high spin configuration. So, so it's a spin 5/2 ground state, and so basically, spin 5/2 ground state, and we applied a spin polarized density states for this, and we find that the manganese dopants introduce two states within like what you normally think of the traditional band gap of the perovskite quantum dot. And then, so And I'm just blanking on how the best way to go through this. So from the spin 5/2 ground state, there's 3 possible electronic transitions we can go through that we can have, which is kind of seen from our orbital diagram, which corresponds to our spin polarized calculations. So for the spin up transitions, we can have a metal to a ligand transition, so MLCT, which is shown in our density states there. And then we can also have a ligand to a metal charge transfer. And those can happen in the spin polarized cases because spin's a good quantum number and you can't have a spin flip in that basis set. But then there's also the possibility of a metal-metal transition. So we can have this spin up, flip up into a spin down. And for that we need to do spin orbit coupling because it can mix spin states and can gives you the opportunity for that transition to occur. And we characterize that in this density state, so we have a metal going to a metal there. And then we also characterize the probability that those are going to occur through oscillator strength, which this plot was a little small. I did this today, so this one. So it's kind of hard to see, but basically what we see is for the metal-metal transitions, there's a very low probability of them occurring, around like 1.8 eV to 2 eV. So we have a small probability of metal-metal transitions. And then we also have, the red line is a small probability of metal to ligand charge transfer. And we also have a little bit higher probability of ligand to metal charge transfer. So basically what we get out of this is that, well, the probability of optical excitations for 3 different transitions that can occur. So that's the ground state electronic structure of the doped system. So we'll move on to molecular dynamics of the system. And what we did is we tracked, same deal as with the intrinsic dot, we can track how the energy states fluctuate in time along the molecular trajectory. And we can see that for the spin up cases, the two topmost energy bands correspond to these 2 states here within the gap. And you can see that the states they don't change at all in time. There's no intermediate trap state that occurs in these systems, which is what you'd expect from a doped system, is to be unaffected by ligands popping off on the surface. So we see no trap states along our trajectory for the doped system. And then moving from molecular dynamics onto our excited state relaxation. So if you look at our red field tensors, you can see in the middle those correspond to non-radiative transitions between the metals, the transition metal dopants. And then an odd thing comparing it with the intrinsic dot is it seems that putting the dopant in changes like the local environment. So you get a different relaxation rate like around the manganese dopant compared to if it was a lead in there. So that's just something we're still kind of looking through to try to explain why that is. And then here is just another excitation from HOMO minus 23 to LUMO plus 13. And in this system, it appears instead that the hole in the electron relax at about the same time, on the same order of magnitude of time anyway, to the gaps. And we see that in the excited state before it relaxes to the HOMO-LUMO, there's quite a bit of emission coming from as it relaxes to the gap. But once it gets to the gap, there's a very faint excitation corresponding to about 700 nanometers, which is a little bit lower than energy than what's experimentally reported for this transition dopant, but about in the right spot, but it's very low over time. And that's kind of the opposite of what we expected to begin with. We expected this peak to be higher over time, just due to the ligands not, or the traps being unaffected by the trap states. So I guess the conclusions from this study so far is that we have to rethink how we're going to or think of a new way to present the results. Because initially we were hoping to show that the dopant would increase quantum yields over time, but either there's something wrong with our methodology or with our intuition going into it about how this system behaves for emitting light. So, yeah, I guess that's about all I have.
Okay, let's thank Aaron for detailed and interesting story. So, other questions?
No questions.
Actually, I have one question. For me, it's interesting because as far as I understand, you work with, let's say, pristine structure of perovskite, right? But did you investigate any defects of this structure, how it can influence on properties of the system, and where you put actually these manganese ions? Where is the position of these ions? Because if you work with doping, let's say, you somehow need to put in good position these ions, right? To make this calculation accurate, let's say. So my main question is, did you try to investigate some defects in this structure?
So for your first question, John has actually investigated defects of just removing a lead vacancy. So he'd be able to explain to you better than I could the effects of that study. But for this, for where I place the dopant, it's admittedly it's kind of hard to see from the figure, but it's basically a 2 by 2 by 2 unit cell, and so really the only place to put it is directly right in the middle, for it to not, because if you put it anywhere else, it would be on the surface. So in this case, it's directly right in the middle of the dot.
Okay.
So you can kind of think of it as like.
So you added these ions. You didn't exchange them with another, right, in the structure, as far as I understand.
Right, we put it in a manganese and we remove the lead. So it's interstitial, or not interstitial, the opposite. Replacement.
Okay.
Replacement.
Hey, Aaron.
Yep.
Question about your format. When this shrinks down to 4 feet by 3 feet, first, is it the right dimensions? And secondly, are your figures going to be able to be recognizable? Because looking right now, they can be easily seen, but if they shrink by 4 times, they're going to be very, very, very small. Or how are you going to like counteract that?
Right. Well, this is a template from someone who's presented at Sanibel, I don't know, like maybe 3 or 4 years ago. So this format has been used before. I guess I can dig around in the office, see if there's posters in there to see how the figures turned out. But yeah, it's something I was thinking about. I guess I haven't gotten to the point of actually like looking at the max, like the biggest size possible for this format. But
okay.
So
just because
I have a comment to Levi. It is not restricted in vertical dimension. So the poster is mounted on about the height of human face, but you can make it longer up to the ground, and then invite visitors of your poster to lay down and watch the lower level.
okay.
Like John posted 2 posters last year, like that.
Levi, do you have questions as an expert in ligand to metal charge transfer states?
Not really.
Okay. John is lifting his hand.
Yeah, okay, so I have a couple of questions. So the first one, and maybe I just missed it, so when you're talking about this trap state, the intrinsic perovskite, did you see something structural that created this trap state, or is it just a weird shift in energy?
It's kind of hard to tell because I think it takes more than one, like pulling off one ligand to create the trap state, it seems like. I think there is maybe 2 or 3 ligands that kind of pulled away from the surface a little bit, and then once it relaxed, like, well, this peak went back up. So
it was almost like an under-coordinated surface atom?
Right, well, more like 3 under-coordinated.
Okay.
Because it seems like it was just more than one of them that was detached.
Okay.
Similar question.
John, would you permit
Go ahead, if you... Yeah, please.
So what's the difference between the left fluctuation and the right fluctuation? It's just 2 different methods or different models?
Okay, so this is the intrinsic, so yeah, it's just the intrinsic one. It doesn't need to be spin polarized.
Okay, so
And
if
then
you,
this one's for the spin polarized with the dopant.
okay, so if you just compare the spectrum, the right one is much more smooth than the left one, right? You do not have any spikes.
Right.
So why a single replacement can cause such a huge difference?
Well, I guess.
Is
Well,
it
the thing is
single
that
run
it's hard. If you're talking about like states that are very close, very packed, it's kind of hard to see when one fluctuates to another.
Can I contribute?
Yeah.
On the rights of author? So there are several unpaired states, and the density of states spin polarized in is unsymmetric. There are some alpha states, and there are no beta states at the same energy. Like there is something going up here and nothing going down. And these alpha states here contribute to the spectrum and some additional fluctuations. And in the beta electrons with spin down projections, just there is nothing in this energy region. Does that answer?
I guess he goes just like these 5 states are going to be the 5 lowest states here, too. So, like, it's going to take a, like, I don't know. Well, maybe it's easier to see in this figure. So, the MN states are so within the gap that any fluctuations due to surface states aren't going to like interfere with these 2 states. Does that make sense? Back to John's question.
Okay. So I've got a couple more. So one of them is figures you have on top for the doped system. Oh, so the density of states for your doped system. So for the spin polarized, you show metal to ligand for the alpha and ligand to metal for beta. But as soon as you go to this spin over coupling calculation, you have metal to metal transitions. And so I'm curious which one you think is accurate.
Accurate as in
Metal.
you cut in and out a little bit.
Oh, so, well, in comparing the 2 density of states figures for the dope system, one shows metal to ligand and ligand to metal.
Yes.
And then the spin over coupling, you show metal to metal. Do you believe one is more correct than the other? Like within the actual experimental system, do you think it's metal to metal? Basically, do you trust the spin polarized or the spin over coupling more?
Well, just knowing the experimental results, because I probably forgot to say in the introduction, but experiment shows that the emission you get from these is about 600 nanometer, which is consistent with DD transitions.
Okay.
And if you look at just the band gaps for the ligand to metal and metal to ligand, it's like ligand to metal is like 3 eV, and then metal to ligand is like 2.4, so that'd be more green. So
Okay.
yeah, it's widely hypothesized it's DD transitions, so metal to metal.
Okay. And then, so my last question is based on the non-radiative and radiative for the dope system. So you're showing, one set of data. Is it for a spin alpha excitation? Is it for a spin beta excitation? Is it a combination of some sort when you're talking about these photoluminescence yields or the integrated emission?
So those are actually computed with spinor orbitals.
Okay.
So it's
then I would, okay. Well, yeah, I guess we were emailing back and forth about that. But then I would definitely clarify that you're using the spinor orbitals in calculation of these type of rates instead of going two different systems, spin polarized fluctuations, and then just relaxation rates. Because I think that'll be interesting for people to see that it's actually spin over coupling.
Mm-hmm. Yeah, I realize it's very ambiguous just looking at it, but I'm just trying to not overwork myself of like putting in comments before I know how it's going to be formatted. So
yeah, okay.
But it's a good idea. You're right to highlight that it's spin orbit coupling, because that's like
because
well,
I think it's much. Yeah, I think it's much more interesting to have that factored in. Oh, and then the last question I have, so with the single dopant in there, is it comparative to experimental dopant percentages that they use in quantum dots?
Yeah, as far as I know, because from what I know, it's experimentally kind of hard to figure out like the doping concentrations. But from just looking at synthesis, it's like mostly all the manganese that they put in, like only a small fraction of it actually enters the quantum dot, so it's very low concentration.
But what is the order of magnitude? It's like 1 to 100 or 1 to million?
Maybe probably more like 1 to a million. Maybe 1 to 100. Well, usually if you have too high of a doping concentration, like the emission changes, it gets more red. Mm-hmm. So you can kind of infer it that way. So low doping will give 600. The higher doping will give more like 700.
Okay, so you're talking like, hundredths of a percent or something like that.
Yeah. I think here it's like, it would be 1 to 500. About. I think that's about how many perovskite atoms are in it.
No.
Okay.
Or is it 300?
Should you count towards total number of atoms or number of lead ions that are replaced?
Oh, lead ions. It would be like 1 in 27.
Then it would be like 4%.
Yeah.
Around 20.
Okay, so that's probably close to experimental then. Okay. Okay, that's all my questions for now. Thank you.
Okay, thank you, John. Are there more questions?
I had a question. What is that little small image right there? What did that represent?
Small image.
On the dope section in between the 4 panels?
Oh, that's my oscillator strengths. Or
it is a vision test.
Oh.
Yeah, it was something I just threw in last minute because I forgot to put them in. And yeah, they need to be in there somewhere. I just threw them in so I can mention them.
Austin, did you have any questions for just education? I have some very basic question. One, to wording of the introduction. At the end of the first paragraph, you tell that manganese makes stable DD transition. What are experimental data? It is just stable or more intense?
Compared to what we have?
No. Purely in experiment. Does manganese make photoluminescence more intense, or it just adds stability?
Both. Well, it does do both.
So it is. It should be substantially intense. Intensity increased due to manganese.
Intensity of
Photoluminescence or quantum U.
I don't know. That doesn't make sense to me because it still emits from the perovskite too.
Mm-hmm.
So it doesn't increase the emission from the perovskite. It kind of siphons emission from the perovskite into the dopant. And I guess I'm not sure what the energy transfer is, whether it's 100% or half.
No, absorbable emission intensity, not the internal processes.
I guess I don't know off the top of my head.
Okay, and a little provocative question, which you may get asked. What is the binding energy of the ligand or pair of ligands? And if it is substantially bigger than thermal energy, how can they desorb during thermal motion?
Well, just from the quick calculations I've done, it's shown to be a couple eV, which is a lot bigger than room temperature.
Mm-hmm.
But that kind of ignores the longer chains of these, because experiment there are like 18 chain carbons, and here we only have 2 carbons, so just the interaction is about a couple eV, but I would assume in reality the longer ligands would contribute to destabilizing, or entropic effects would decrease the binding energy.
And without an argument to experiment, you're computing binding of about 2 eV, and then you are observing molecular dynamics with ligand desorption. Are they in contradiction? Do not answer, just keep thinking, and it is standard question that people ask when trying to